9. The last lesson in chapter 3 is entitled 3.4, Using Exponents to Solve Problems. I'm going to launch into that now. After this, really all that's left is review. So we'll get going. And this is going to be one of your favorite sections, of course I know, specifically word problems. Yay! That's okay. That's what I'm here for. We'll make these make sense, not to worry. We've gone over the exponent laws, including BEDMAS, in lesson 3-3. If you haven't gotten through 3-3, or if you've been away, that's the whole point of this video series. Go back through these and get a chance to go through it, grab a notes blank, fill it in, and you should be able to get right onto your assignments. At the end of almost every notes blank is the assignment for MathLinks 9. So what's the big idea here? Solve problems that require combining powers, use powers to solve problems involving repeated multiplication, and I dare say that you'll get a chance to see patterns. Let's get going. Now, volume of a cube. Interestingly enough, we talk about televisions these days, 3 dimensions. It's all the rage. What do they mean by 3D? Well, in order for somebody to be, or something to be 3-dimensional, you have to have length, and you have to have width, and you have to have depth. And that's you taking up a space in the physical universe. For those of you who are wondering, by the way, the 4th dimension is time. If you like that kind of thinking, go check out Physics 11. There you go. There's a little plug for Physics 11. A volume of a cube, well, we've done this one before. I think it's all been drilled into our heads a million times. So I'll draw my best cube, my stylus here. And we have length, and we have width, and we have height. It really doesn't matter which way we think about this, because it doesn't matter what order you multiply in. Length, width, height. So if the sides of a cube are 4 by 4 by 4, by 4, and 4 deep, if you want to think of it that way, then what we've got, and let's say these were in centimeters, we would have 4 centimeters times 4 centimeters times 4 centimeters. Another way of writing that, and I'll just sneak some space here, 64 centimeters cubed. Well, I always think that's kind of interesting because we were looking at a cube to start. A cube is a classic introductory definition of something which has 3 dimensions. And we have that little formula burned into our head, length times width times height. It's really just a multiplication of the dimensions. Hopefully that was a pretty straightforward one. Little warm-up. Example number 2, the bacteria question. This is a really neat example. I'm going to pop out into a different color. Choose a blue here. A colony of bacteria triples every hour. If you look at bacteria, instead of doing sexual reproduction, if they find a food source, they will just clone themselves like mad to increase their population super fast because they're trying to take advantage of all that food. And that can be bad for us, right? That can affect a cut. It can be quite nasty. Let's say you start with 30 bacteria. And that triples every hour. So we'll take the 30 initial bacteria and we'll say 90. Okay, so what we talk about is every hour it triples. So an easy way to think about this, what was the initial population? It was 30. And then it triples every time. That's like multiplying by 3 each hour, right? So 30 times 3 for the first hour, and then times 3 for the second hour, and times 3 for the third hour. That's exponential work, right? Where we have multiply by 3, multiply by 3, multiply by 3. Let's get into that. Change color here. Let's go with the regular blue. So we can say it started with 30, and depending on the number of hours you have, Here it is at 90 after the first hour. And here it is after 3 hours. And if I keep going, we've got 6. This is it after 12 hours. It's tripled 12 times. There's an easier way to write this. If we say that the number of times it could triple could just be given the letter, let's hit done and choose a different color. If the tripling time was given the letter n, like this, we could say in a general way that the formula is the initial population, whatever it is, times 3, and the exponent is whatever the number of hours is. So in the first hour, we had 30 times 3 to the first. There we go. 30 times 3 to the third power for the third hour. Run out of room here, so I'll go up here. 30 times 3, 3 multiplied by itself 12 times. It's a pretty neat formula. If we apply this in a very generic way, what we've got is just a simple overall formula. The initial population we said was 30, but that could be just about anything. So there's a neat little example here. There's like n something to the h. Let's just scribble that out for a sec. What they're trying to express as a formula here, if we went in a really basic way, is let's let something represent 30. N times 3 to the h. There you go. There's your basic overall formula, where n is the number of bacteria that you begin with. And it triples, and for every hour it triples, you get this incredible graph where the population just takes off like this. It's called an exponential increase. And it can't go on forever because the bacteria run out of food, and then it crashes and it comes right back down. Sometimes it bottoms right out. So this is a really powerful question where you see a formula pop out like this. And it gave us, because n was 30, it gave us a really simple way to figure out how many bacteria there would be, no matter how many hours went by, because each hour was just a tripling. It was so convenient of them to tell us that the initial population was 30. That's just something you multiply with. Good question. It comes up in your assignment. Surface area. You might remember total surface area. Maybe it brings back nightmares from grade 8. Not to be feared, not even in the slightest. Why? Well, because the surface area of a cube, think about a cube. I always like to tell my students, they're like dice. And dice have 6 faces. There is a top, bottom. There's a front, back. And there's a left, right. But the neat thing about dice is they're all the same. They're all squares. If we look at the surface area of dice, and we know there's 6 faces, there's 6 faces times whatever the length width of each face is. So I'll just draw it like this. Length times width. Because this is a square, one thing we can do, instead of writing length times width, we know they're the same, is we can just say that they're side times side. When you see that done, don't let it throw you. It just means that they're the exact same value, so we give them the same letter. So the surface area is 6 of the faces times 6 centimeters by 6 centimeters. 6 by, think about it, right? The area inside was 36 units squared. 6 by 36 centimeters squared. And if that doesn't come to you right away, grab your calculator or do the good old-fashioned mathematics you were taught as a kid. 6 times 3 is 8, carry the 1. 3 times 3 is 9. 108. Okay, fine. This is 108 centimeters squared. And remember, they were asking you about area, not volume. Therefore, that unit makes sense because there's only 2 units being multiplied in area, this side and that side. And it's really nice when you're dealing with rectangles and squares and things like that. Along came Pythagoras. This question, I saw this and I was thinking about this with my lesson. Wow, it's been a little while since students have seen Pythagorean Theorem. Okay, I'm going to go back briefly over Pythagorean Theorem for those of you who've forgotten it with a scalene 3, 4, 5 triangle and just remind you for a second where it came from and the wonder of Pythagoras scratching these symbols in the dirt and getting this correct. So let's use a nice, appropriately annoying brown. If we look at a triangle, try to draw it manually to scale. Let's say that this is 3 units high and 4 units wide. So if we drew a square, and that's exactly what Pythagoras was saying, what if we drew a square off the side? So it's 4 rows and 4 columns. If it's a 4 by 4 square, there are 16 units inside here. 16 units. So I'll just make that nice and brown so we can't miss it. It has an area of 16, but I always say that count 16 little squares. The same thing applies if you draw a square off the side. Ooh, let's undo that. If you draw a square off to the side of this, we're talking about 3 rows, 3 columns, or something with an area of 9 units. What Pythagoras said is if you took the area, the 9, and you added it to the area of the other small square drawn off the 2 smallest sides of the triangle, they added up to this one we call the hypotenuse, right? It's across from the right angle. It's the slanty one. And what he noticed is 9 plus 16 equals 25. So I'll do, I think I've got 5 by 5. We'll make this look as good as we can. And there we go. And this had an area of 25 fabulous units, which means the square root of 25 is, well, that's 5. And the square root always tells you the legs or the side of the triangle. So this is a 5 by 5. Oh, there we go. And discovered this idea that he called Pythagorean Theorem. A squared plus b squared equals c squared. Where a and b are the 2 short sides of a triangle and c is the hypotenuse, Pythagoras discovered that this works for right triangles. And pay attention because this is a formula. 9 plus 16. Does that equal 25? Yes, because, ooh, get in there, you. 25 equals 25. Yeah, awesome. Now, Pythagorean Theorem, I have a whole bunch of erasing to do here, is formulated off this idea. So, go back. What we'll do in the example that we have a 9, the legs are 9 and 12 of the triangle we're looking at. So, look at that, the magic of undo erasing. What is the hypotenuse? Well, if we drew squares off the side, just like we were kind of talking about, if this was a 9 by 9 square and this was a 12 by 12 square, not drawn to scale, mind you, those 2 little squares should add up to that big square's area. So we'll say the formula is a squared plus b squared equals whatever the hypotenuse is, right? The square off its side. 9 squared plus 12 squared equals the square you'd make off the long side, the hypotenuse. 81 and 144, so those squares equal a combined area that would equal the big square. 144 and 81. Let's crank that out. 225. Interesting. If you hit the square root of 225, or if you just know two values that when multiplied give you 225, here's a hint. Think 15. You have your answer. C squared is 225. We need to undo c squared. The opposite of multiplying two values together is to hit square root and find what one of those identical values would be. 15. So our missing side is 15. So this square would have been a 15 by 15 square. As Pythagorean theorem comes up, we'll hit it again later on in the unit. This is one of the questions where you really just hit square root at the end once you add up the two smaller squares and figure out what the hypotenuse's length would be. But remember that there is a subtraction game that can go on. If you know the hypotenuse, you can square it and subtract its answer from the square of any one of those sides to find the other one. It's just the trick that two things add up to be another thing. So you can take the answer and subtract the one you know and find the other missing one. It will come up. But we don't want to diverge into Pythagorean theorem for the whole lesson. Composite areas. Composite is just a fancy word which means which means two things. So two things being considered in an area question. A circle inscribed with a square. What the heck does that mean? It means inscribe, right? Like scribble. There's a circle inside of that there square. And what's happening is the square has an area of 16, or has a side length of 16. Let's go back. Let's go blue this time. So we know that this is a 16 by 16 square. Well, one thing I know about circles, they're kind of like the spokes on the wheel of my bike. If that's 16, where's the middle of my bike wheel? Right about there. So this is probably, well, not probably, is definitely a radius of 8 centimeters on either side, and we refer to that as half of the diameter and half of the diameter's radius. So you write down the values you know. You say, oh, wait a minute here. I know that radius is equal to 8, so diameter is equal to 16, and you scribble that down on the side, and you have a little bit of information when you need it. This is the kind of question which gets you to think about, well, what would happen if, let's see if I can go to erase. There we go. Never erases fast enough for my liking, but I can get rid of it as best I can. There. If we had a 16 by 16 square, we know that the area of that square, and I like to draw it this way, is 16 centimeters by 16 centimeters, which is good for 256 square units. We're talking about centimeters. Nice. And remember, the reason we write centimeters squared is because there's two identical values there. That's where this part comes from. You want to subtract the area of the circle because it's like you cut a circle out of the middle. Well, the circle's area, you might look at it and say, geez, I don't know what it is. Well, the circle area of a circle is the formula pi r squared, which is, pi is 3.14. You could get away with 3, but let's be kind of exact. Let's say 3.14, and we know that the radius we wrote down. Don't put diameter, because if you put diameter, when you're using diameter, you use that for things like circumference. But when area, it always comes down to area. Think of the R in area. It always reminded me. The area is 8 centimeters, and that gets squared. Now, so we'll pop out. This is 3.14 times 64 square centimeters. I don't have that memorized. So I'll pop out to my little calculator. Neat little application. This is a good little app. And let's erase that. 3.14 times, and we were looking at 8 times 8, we get, well, let's call it 201. So 201, pop out to our example. We need to subtract these. These were what we were looking at subtracting. And this makes a lot of sense because all that's left of our answer, all that remains, is just this little bit of the original square. The rest got chopped away while we were doing some work. So there shouldn't be very much left. In fact, all that you've got left, 256 minus 201, is around, we're doing a little bit of rounding here because I said 201, which is good enough, 55 centimeters squared. So that's a good question where you have to take one formula and subtract another. It's a very good question. Healthy. It's a question where you've got to figure out something and then keep moving forward with it, and that's why you need to get really good with just your basic mathematics, because it all starts to move together. Okay, so at this point, I'm going to call this, going to pause this lesson because there are combination problems that we still have to do. So I'll be back in a little bit. Have a good one.